All right. Hello. We'll wait a minute or two for some more people to join. Nice. Okay. So, let's get started. Let's review the definition of a probability distribution. So for instance, a probability distribution is a sample space along with the function p, so that all the events have a probability of between 0 and 1. And the most important thing is that the probability of the entire sample space is 1. So we can just assume that the probability of the null set is 0 usually. And normally, if we can define the probability of individual events in the sample space, we can assume this formula is true as well. Okay. So let's say that we have a set of n trials where we want to have k successes. So let's talk about what this means. So when we say n trials, we generally mean that there are n independent trials and these trials are, so by independent we mean that they don't interfere with each other, and we also mean that they have the same probability of success. And so what we mean by success is that basically one of these trials will either result in, so each trial will either result in success or failure. Now, it depends what we mean by success or failure, and it'll define by the problem. A lot of times you can always pretend that success is either hitting the target and failure is not. Or, you know, success could be that a certain drug works, or that somebody picks a certain thing, or that a coin flip goes a certain way. Whatever it means in the case of the problem, that's what a success is going to be. And a failure is just going to be not a success. Very good, Kevin. So the idea here is that either we have success or failure. Each one of them has the same probability. Let's call that probability P for the probability of success. So this is called the binomial distribution. So we remember, well, we'll use that in just a second. So we're going to assert that the probability that there are exactly k successes, so this is usually the notation that some statisticians use for exactly k successes, is equal to n choose k, p to the k, q to the n minus k, where q is 1 minus p. So, yeah, sorry, he didn't join in today. Okay. So, basically, we want to show that this is a probability distribution. Q is equal to 1 minus P is just notation. I mean, you can not even talk about it and just have 1 minus P to the n minus K. Basically, what this is saying is that the probability of having K successes is, if the probability of having one success is P, then the probability of having K successes is P times P times P times P, K times. And we're having n trials, so we have n total trials. And so what we're going to end up with is 1 minus P times 1 minus P times 1 minus P, all the way down a whole bunch of 1 minus P's, n minus K of them. And so this is the way that you can have K successes and then n minus K failures. So why do we have this combinatorial term in front of here? Why do we have an n choose K? The answer is we want to know how many possible different ways that we can get K successes and n minus K failures if we're allowed to jumble these up. Well, he's sort of here. Does he want to call me on now that he's here? Okay, hey Ben. Let me unmute your desktop audio. All right, there you go. I think you're unmuted now.
Oh, great. Are we shooting arrows at the thing?
Well, we're almost there. I'm deriving the formula.
Oh, okay. So we're pulling the string back, ready to let loose a formula.
Yeah, basically.
Okay, cool.
So what I've given them so far is that if you have P successes, or I'm sorry, K successes and n minus K failures, then you have the probability of P is the probability of success. So you're going to get P K times and 1 minus P n minus K times for n total trials.
Yeah.
And then I've said, but wait, there's more, you know?
Oh.
Because,
You really made them?
well, because the thing is that if I multiply P together K times and 1 minus P n minus K times, then that is the probability of getting, for instance, K successes and then n minus K failures in that order, right? Whereas we just want we want the probability of getting K successes regardless of the order. So the question is, how many ways can we jumble up
all of our successes?
Yeah, the successes into the total number of trials. And so the answer is
this is a lot like that light switch thing, right?
In fact, it is exactly the light switch thing. Out of n light switches, we pick K to be on, and then we stick that in front of the whole formula. And so that's how we get this this thing here, which is the definition of the binomial distribution. That's okay. Beautiful. So, let's do ourselves a quick proof. It is 1 minus P, because if P is the probability of success, then 1 minus P is the failure. P is just a probability. Okay, so let's prove that this thing is in fact a probability distribution. Well, so most of the axioms for probability distribution are going to be satisfied. So like the probability of the null set is kind of we can just assign that to be 0. There's no problem with that. The union axiom is going to be okay because we're dealing with the probability of individual events. The real thing that we have to verify, the important thing that we
bit. I think it's still sleeping on it.
Yeah. Something is up.
It's back now, in part, for me.
Okay. Yeah, I'm not sure. It was kind of rebelling earlier today, too.
Is it because I hacked your system? That's because I got here, isn't it?
I can't blame it on you because it was doing it in 201.
It's been doing it to me. Maybe the tubes are full.
Yeah, it could be that there's some issue with YouTube
Do you have the
streaming.
extra low latency selected?
I do have extra low latency selected.
I just started using that and I had this problem more, so I wonder if going to the middle setting would help it. It adds more lag, but anyway. We're already committed, so...
Yeah, as it turns out, I can't change that now because it's grayed out. Can't do anything. Okay, so... Yeah, alright, so let me just go over... I don't know how much people missed. I just realized, I looked up and saw that the stream was wonky. So basically, the probability of the empty set is 0. That's an easy one. We don't really have to check that. Really, the two things we have to check are that all the probabilities are between 0 and 1. And we have to check that the sum of the probabilities is equal to 1. We want to check that it's like a true distribution. Okay. So let's do the probability between 0 and 1 thing. So is it true that n choose k times p to the k, q to the n minus k, where q is 1 minus p? The only reason why I use this q variable is because you'll see this in a lot of textbooks. You can just as easily replace q with 1 minus p and it's fine. So is this bigger than 0? And is it less than or equal to 1? So a null set is just an empty set, right? It's a set with no elements. Anyway, okay, so is this thing between 0 and 1? Oh, I see. So that's actually Well, I'm not going to prove that it's less than 1 directly. What I am going to do is I'm going to prove that it's bigger than 0. And that's just because n choose k is bigger than or equal to 0. The probability p has to be bigger than 0. And therefore 1 minus p has to be bigger than 0. Technically, this has to be between 0 and 1, and this has to be between 0 and 1. So these two terms are going to be between 0 and 1, but then you're multiplying by this term. So technically, this term doesn't guarantee we could get above 1 if we weren't careful, but we never do. And the reason why is because since all of these are positive, we just have to add them up to prove. So if we add them up, we start at 0 and go to n, and we add up n choose k, p to the k, q to the n minus k. And as it turns out, the reason why this is called the binomial distribution is because this is exactly the binomial theorem. So if you remember the binomial theorem, it says that p plus q to the n is equal to the sum from k equals 0 to n of n choose k, p to the k, q to the n minus k. Oh wait, that is exactly this formula. So the binomial distribution basically tells us exactly what we're doing here. So we say p plus q to the nth power. And so what we can do here is remember that q is 1 minus p, so we're going to have p plus 1 minus p to the nth power, which is equal to 1 to the nth power, which is equal to 1. So as it turns out, the binomial distribution is in fact a probability distribution. And we've proven it by basically just a direct application of the binomial theorem. Okay. So that's some boring stuff. So the only reason why I go through this is I'm going to ask you to prove that the expected value of the binomial distribution is NP on your homework. And I have a little guided exercise that gets you there. Okay. So let's look at some example problems.
Wait, how did we get 0? Can you? How did we get that it's 0?
Which thing is 0? What thing is 0?
The null binomial is 0.
So this says, okay. So basically, the probability of some number k is equal to the formula, right? And so if you don't stick a number k in there, if you actually say, because this is really saying the probability of the set containing k is this formula. Now here's the thing, what if I say the probability of this empty set, right? Well, it doesn't have anything in it, so basically we just define it to be 0.
Okay, so it's that way because it be that way.
Yeah, so it's a definitional requirement in terms of a probability distribution, but I'm not sure if people actually heard me, but the point is that normally you don't have to verify it, because if you define the probability distribution in any way that makes sense, this will kind of just automatically be true, and if it's not true, then you don't have it, then you're in trouble. So yeah, so basically the point about that is that the probability of the null set is 0 just because the null set is not some integer k, right?
So when we say there's no trials, there's no probabilities. Like if we define it that way, then that means that we satisfy that constraint.
I suppose.
There aren't any trials, there's no probability of anything. Okay, all right.
Yeah, I wouldn't think too hard about it.
But it hurts. Okay.
Wait, are you really thinking hard about the probability of the null set?
No, I'm not thinking hard about it. I get it. I got it. Basically, the idea is we define the probability distribution.
Basically, I'm defining the probability on all the integers k from 0 up to n, right? And so those are the elements of my sample space. And the question is, what if I take the probability of none of them? Not 0, right? 0 has the probability. There's a probability of no successes. But this is not the probability of no successes. This is the probability of literally the nothing set. So none of these integers. And so the answer is, if probability is defined only for these integers, then we can probably assume that the probability of nothing should just be 0.
Cool.
Yeah. Okay.
The probability that there aren't any successes or failures is 0 because there will be successes or failures. Got it.
Yeah, something like that. Okay.
Something like that. Okay. Groovy.
Okay, is that going to click or is it not? It's kind of rebelling. Huh. Weird. Come on. Ooh. Maybe my internet glitched because the live board's rebelling as well. It's not happy with me.
But I consistently got your talking to me over Discord, so.
Yeah, but I can't click on a different page.
Discord is pretty magical in its ability to stay connected, though. So.
Okay, so there we go. Now I can click on a different page. It wasn't letting me do anything. Okay. So here's the simplest example. So the point of the work that I just did was to prove that the binomial distribution is in fact a probability distribution. So it doesn't really matter for what I'm about to do, and so, yeah. Okay. All right. So we flip a coin 5 times. I'm going to say the coin is fair. When I say the coin is fair, what that means is that the probability of success is going to be 1/2. Because a coin has 2 sides, and so the probability of success of a fair coin, I guess a success in this case is heads, right? Is going to be called success. Of course, in a different problem, heads could be failure. It doesn't really matter as long as something is defined as success and something is defined as the other thing. So in this case, we're going to define the probability as 1/2. So that also means that Q is equal to 1 minus P is 1 minus 1/2 is 1/2. Not surprising. So, okay, what is the probability of 3 heads? So 1, the probability that we get 3 heads. So let me distinguish this again. So this is the probability that we get 3 heads. So 3 heads can occur in a bunch of different ways. So we're going to use the formula. It's going to be 5 choose 3 times 1/2 cubed times 1/2 squared. So you notice that in this case it's just 1/2 to the 5th because the powers will add. The important thing is that we do this 5 choose 3 business. So actually what we're really going to get is 5 choose 3 divided by 32. Yeah, so the first question is, what is 5 choose 3? Well, as it turns out, it's 5 times 4 times 3 times 2 times 1, right? 5 factorial over 3 factorial times 2 factorial. So we cancel, 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 and that leaves us with a 2. So this leaves us with 10 out of 32, which is equal to, I guess, 5 over 16. So that. Okay. So let me just say, this is a different thing than asking what is the probability that I get exactly, say, heads, tails, heads, tails, heads, right? The probability of heads, then tails, then heads, then tails, then heads is exactly 1 out of 2 to the 5th power. The distinction between these two things is that in this case, we have 1/2 to the 5th power because we have a specific order, right? Specific order. In this case, we have no specified order. So what we are going to consider is all possible orders of 3 heads and 2 tails. So you can get heads, 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 tails, tails, right? There's 10 different possibilities, right? You can get like heads, 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 tails, tails. You can get heads, tails, heads, tails, heads. You can get heads, tails, tails, heads, heads, and 7 more. I'm not going to list them all out. But the point is that there are 7 of them additional. I guess I should say plus 7 more. Okay, so that's the difference between these two things. So one of them is actually just a straight up multiplication principle like we talked about in the past. The other one is the binomial distribution. Okay, cool. So now what's the probability of all heads? It's 5 choose 3 because you want 3 heads? Yes. Can you do this with a permutation? So the binomial distribution is defined with a combination. I'd have to think about it to see if you could replace this with a permutation and then make it work. I think you would have to still do some correction terms and stuff like that. So I'm going to say use the combination formula. So the probability...
Wouldn't a permutation question be like, how many different ways could you get heads 3 times, like in the ordering?
Well, sadly, that's actually what this 5 choose 3 is answering. Because if you draw out 5 spaces, and you say that what we need is to pick 3 of the 5, right? Then this is space number 1, this is space number 2, this is space number 3, space number 4, and space number 5. And so the thing is that this is known as a 5 choose 3. The other way to think about it is, it's not a regular permutation. It'd be a permutation with indistinct elements.
Oh, yeah.
So, How do you do that? Well, you write out the word that you want to permute. HHHTT is the word. And then you count up the number of repetitions. 3 times heads, 2 times tails, and then you write 5 factorial over 3 factorial 2 factorial. So actually this 5 choose 3 is a permutation of sorts. What it is it's the number of distinct permutations. And so that's why it's a combination in this case. It just happens that the number of distinct permutations where you have 2 letters is the same thing as the number of combinations of picking out of the bag 3 things out of 5 things. So it's kind of a convenient accident that this is the combination formula, and so we just use the combination formula. Okay. Yeah, if you had like 3 different things, say you had, A's, B's, and C's in a word and you had to permute them, then this would no longer be a standard binomial combination. It would actually be something called a multinomial combination. So you'd have like N choose K, J, and L. So it'd be more complex. All right, so let's get back to number 2. What is the probability of 5 heads? Well, the nice thing about this is it's 5 choose 5. Oh, I think some people were answering some people were just saying what the answer was, and I was kind of ignoring it because I was answering a whole bunch of other questions, but yes. So it's 5 choose 5, 1/2 to the 5th power, and then 1/2. I know that this is kind of pointless to write this out, but it's 5 minus 5, right? N minus k, where k is equal to 5, and n is equal to 5. So it's 5 minus 5, so the power is 0. So overall, this 1/2 just gets to the power 1. I'm sorry, not to the power 1. It gets to the power 0, which is 1. So, and then the other question is, what is 5 choose 5? If you have a bag of 5 things, and I ask you how many ways can you pick 5 of those things out of the bag, the answer is 1. You just pick everything. And so then this is 1 times 1 over 32. Cool. All right. Let's do the one last problem. So what is the probability of between 2 and 4 heads inclusively? So the probability that 2 is less than or equal to x is less than or equal to 4. Let's do this on a separate page because I'm running out of room. So remember that p is equal to 1/2 and the number of trials is 5. So basically here, this thing is just going to be a sum of the binomial formulas. So you're just going to get 5 choose 2 plus 5 choose 3 plus 5 choose 4. And then here you're going to get 1/2 squared, 1/2 cubed. Here you're going to get 1/2 cubed. Whoops. Jumped ahead of myself. 1/2 cubed, 1/2 squared. And finally, 1/2 to the 4th power, 1/2 to the 1st power. So if you guys are wondering how I'm computing these terms so quickly, just remember that these 2 powers always add up to 5, and the first one is the number of successes. So I don't need to think about the formula too hard about like, oh, this is n minus k, this is k. I just go, okay, this one's 2, they have to add to 5, so this one's 3. This one's 3, they have to add to 5, this one's 2. So I'm not really thinking about some like really complicated thing when I'm doing this. I'm just kind of writing out all the possibilities. If you're really concerned about it, I mean, you can always write something like so as it turns out, it doesn't really matter if the probability of success and failure is 1/2, then you don't really have to care about this. You can just combine these terms. Yep. So yeah, this is basically the probability that x is equal to 2 heads plus the probability that x is equal to 3 heads plus the probability that x is equal to 4 heads. I'll just draw a line here. But yeah, these two things are equal. So, yep. Okay, cool. So that's actually not so bad. So I guess the question that you guys might have is like, what about on homeworks? Are we required to evaluate these terms? The point is on homeworks, quizzes, and exams, you're not required to evaluate. Now, if you want to evaluate, there's nothing wrong with that. For instance, you know that 5 choose 2 is the same thing as 5 choose 3. They're both 10 out of 32, so we get 20 out of 32 plus 5 out of 32, which is 5 choose 4, divided by the 32 business, which is 25 over 32 total. So that's the actual number. But as I say, you are not generally required to evaluate these, especially if the formula is at all complicated or requires a large amount of calculations. This one's generally doable. Okay. Well, so yeah, I basically should just tell you. Yeah, we're getting. I think I basically said we're getting rid of quizzes. So in terms of exams, I was thinking of releasing a take-home exam on next Wednesday, and you would have a week to complete it. All right. Oh God. My stream is still live.
Mine errored out. I had to refresh.
Oh, good God.
I know. The tubes are trying to die on us.
Well, the good news... Okay, I'm going to write it down. Exam next Wednesday.
Yeah, it looks good now.
Exam is next Wednesday, people. I'm going to send out an announcement, too. But it's going to be take-home. Which means you'll have 1 week to do it. I don't know what it would be if I didn't say it's a take-home. I think everything's a take-home now, right? I think that's by definition, but, you know, this is a math class, so... Okay. All right. No. It's going to be released as a PDF. So you will have literally 1 whole week to work on the problems. So that means everyone's going to get 100. And I'll be very embarrassed for making an exam that was too easy. Okay. Yeah, I'll try to release a practice test tomorrow, maybe, possibly. Okay. So let's look at this one. If we shoot 20 arrows at a target and we want to get at least 18 hits, then if the probability of a single hit is 95%, so we're a pretty good shot, then what's the chance of at least 18 hits? Yeah, so no. As of now, there's no such thing as quizzes. Okay. Yeah, quizzes are DNE. So, okay. We want to know what the probability of getting at least 18 hits is, so remember that at least 18 in this context is going to mean 18, 19, or 20. Yep. Your grade is homework and exams now. Okay. Okay, so, right. So let's compute this. What is the probability that x is bigger than or equal to 18? Well, it's equal to C20. Oh, wait, what am I doing? Not C20, 18. 20 choose 18. 0.95 to the 18th power. 0.05 squared. Well, quizzes that you previously took count, of course. Not eliminating previous quizzes. I should say, in the future. Fine. Okay. I don't know why you guys are going into computer science. You should go into the law.
Are we shooting the arrows now? I'm very excited.
I'm doing my business. I'm shooting the arrows. I'm shooting 19 on target now.
We're shooting 19.
Yeah. So we did 18 here. This was 18 on target. And now we're going to do 19 on target.
Stay on target.
Almost there.
Almost there.
Stay on me, Porkins.
Don't get cocky, kid.
It's just like hitting what are those things back in the canyon?
Womp rats.
Womp rats, yeah.
Womp womp.
So, the target is a 1 meter wide vent on a large sphere. Yeah, Beggar's Canyon, exactly.
Beggar's Canyon, thank you, nerds. This is why you're nerds and wonderful.
Oh yeah, no, I made a mistake in 201 about the difference. I said I attributed a quote to Obi-Wan that was attributed to Qui-Gon, and oh man.
Woo.
I was informed of my error very quickly.
Woo! And you made it out of the room alive?
Well, you know.
You weren't the same. You seemed different afterwards.
Yeah, you're never quite the same after something like that.
So this is how many womp rats we kill? No.
Yes. We have, Luke has shot at least 18 of the 20 womp rats, and the probability is this. Now, you see that actually calculating this can be a little annoying.
Just a little bit.
Well, I guess it's fine. I mean, it's not really a problem. I guess a Windows calculator is still capable of it. Well, because you can calculate 20 choose 18, by hand. By just doing 20 choose 18 is equal to 20 times 19 divided by 2. Which is whatever that is, I guess.
4. It's greater than 4.
Well, it's quiet you. 10 times, it's 190. Right?
Which is greater than 4.
It is bigger than or equal to 4, yes. Thank you, Ben. Your contributions are...
I'm adding value!
Yeah. I mean, granted, now I thought it was just the students trolling me in the chat, and now it's you too. Everybody's trolling me. Apparently I'm an easy target. So, okay, and then we just do this business. 0.05 squared. And so we see that this number is probably not going to be very big, because 0.05 times 0.05 is already 0.0025, and then you multiply by 0.95 to the 18th power, which is small, and then you multiply that by 190. So I'm getting something approximately 0.18867 for this one. All right, so now let's see what we get for the next one. The next one is 20 choose 19. So 20 choose 19 is just 20, because that's saying out of a bag of 20 things, pick 19 of them. So basically that's the same thing as picking one thing and discarding it. So that's 20. And so then you're going to multiply that by 0.95. Ooh, beautiful. So does anyone know what 20 times 0.05 is?
It's not 4.
Thank you.
Or greater than. It's 1. Is it 1?
It is actually 1. So that's isn't this beautiful?
My gosh.
Isn't this beautiful? Because now we have a 0.95 to the 19th power, and the rest of it's just 1, so we can kind of ignore the rest of it.
Oh, that's beautiful.
Yeah, exactly.
You know what always kind of upset me, and still kind of does, is how 0.05 squared is not 0.25. Like, it makes sense, sort of, but I really want to use that extra decimal place to the left. It's spooky. But I can't. Math won't bend to my will. I must bend to its.
Yeah, I mean, 0.5 squared, right, is 0.25.
Right.
So that's happy. But 0.05 squared
is not 0.25.
No, that's equal to, I mean, really you can even just view it as like 10 to the minus 1 or 10 to the minus 2 times 5 squared. So that's equal to 25 times 10 to the minus 4. So that's why you get so many decimals.
You know, this makes me a bit more comfortable.
Yeah, I figure when you separate it this way, you'll like this one you don't like. This one you do like.
Yeah. See, you should be some sort of like, you know, you're not should be. You are some sort of math whisperer. You've taken my math.
I should teach this.
But no, it's not just teaching that you're doing right now. You're finding me comfort in the world of math.
Oh,
so
yeah.
You're not just teaching me. You're taking me on a guided tour of your love of math, and I appreciate that.
Oh,
anyway,
you're welcome.
I'm sorry to interrupt. You keep guiding us on our math tour.
All right, so
Let's
we're almost
some more rats.
Yeah, we're almost done. So the last thing we have to do is compute 0.95 to the 20th power, which is the main reason we're having this discussion, people, is that when you're doing calculation, it's boring.
It's true. It's very boring.
Yeah, so calculation is boring, and this was less boring.
Marginally.
0.9245. Excellent. Okay, cool. Oh, man. Okay. So, let me tell you about expected value, because that's what this slide is about. So the expected value of an event. Yeah, we should do some co-op Portal 2.
Yeah, I'm down. You tell me the time and the place, and we'll set it up on the WWs.
All right, I gotta do some. Yep. Hang on.
Is there a dog happening?
There is a dog.
Do I have to take over? Is
Nope.
it my turn to math?
Nope.
I'm not ready for this.
Why don't? Yeah. I can't go on, Ben. You have to do it for me.
No. I teach the programming. You teach the math. I can't. No. You even do the programming. I'm lost.
Okay.
Okay.
So let's define expected value.
Oh, please. Yeah, I'm going to go back to my hole.
Okay. So we know that if you have a probability distribution, okay, well, that was a terrible summation symbol. That's better. the summation of the probability that x equals little x over little x inside the sample space is 1. That's the definition. That's the definition of a probability, or part of a definition of probability distribution. On the other hand, this formula with expected value adds an x in here. And so the reason why it does that is that we multiply each probability by the value that that probability has. So we have to assume that these we have to assume at least that, so this is unfortunately, I'm introducing this because this is statistical notation. I generally hate this, but notice that this is an uppercase x and this is a lowercase x. So basically what statisticians mean by this is our variable, and this is the value x, and the value x is still lowercase here. So this is lowercase here, but uppercase here. And you might think, like, this is horrible. Why would anyone do it this way? The answer is mathematicians would not, but statisticians write this all the time. They like mixing upper and lowercase variables of the same name. I mean, it's sinful.
Would you say it's heresy? Or is it just...
I mean, it's heresy to a mathematician. Like, a mathematician would be like, there's plenty of letters in the alphabet. Why would you do this? The answer is statisticians, I don't know. They don't care. They do whatever they want.
So you would... Who's the more case-sensitive group? Statisticians or mathematicians?
I would say statisticians are the people who care, who are the ones who introduce upper and lowercase variables all the time like this.
Yeah, so they're the sensitive.
They're the case-sensitive ones, yeah.
The case-sensitive lot. Whereas mathematicians are like, yo, we'll just use some other letters.
Well, mathematicians are generally like, we just won't do that. We'll just use the lowercase x and then not use the uppercase x. Or if we do, we'll do something smarter about it. Okay, anyway.
Your opinion's leaking. All right, back to my...
Yeah, exactly. So that's the expected value. So let's do a simple calculation of the expected value in this case. So let's say that a person selects a set of 2 balls at random. What is the expected value of the sum of the numbers on the balls? So here are the values in the urn. And so, okay, so what if we just did, let's simplify the problem and say we select 1 at random, and then we'll get back to the 2, okay? So first we do 1, and so what is the expected value of picking 1 ball? And so the answer is that the probability of picking any given ball in this case is just going to be 1/5, right? Because let's just say that all of them are equal. You can't tell the difference when you're reaching into the bag or the urn. And so you can't tell what you're about to pick. So you're either going to pick a 1, you're going to pick a 2, or you're going to pick an 8. And so, okay, what is the expected value of this? And so the expected value of this is 1 times the probability that we pick a 1 plus 2 times the probability that we pick a 2 plus 8 times the probability that we pick an 8. And that's it. So the real question is, well, what are these probabilities? And they're not exactly 1/5 anymore, right? Because the probability of any given ball is 1/5, but there's 2 2s and 2 8s. So the probability that x equals 1 is 1/5, like this. But the probability that we get this one is actually 2/5, and the probability of this one is 2/5, like that. So we're going to get 1 plus 2 times 2/5 plus 8 times 2/5. And so what is this in total? This is 16/5 plus 4/5, which is 20/5, and then that's 21/5. which is, what, 4.2? Okay. So, one thing to say about expected value is that the expected value, you notice that it's not a 1, a 2, or an 8. So expected value is an average of values. What it really means, what expected value really means is not, if I run this trial once, what do I expect to get? Because you don't ever expect to get 4.2, right? Because your answer is either going to be 1, 2, or 8. So your expectation if you do the trial once is either a 1, a 2, or an 8. What we mean by expected value is if you run the trial, say, 1,000,000 times, and then you average the results. So you can get the expected value. It's possible that the expected value could have turned out to be 2 or 8 or 1, theoretically. In this case, it's not, but so you can't expect to get the expected value. But what you do is the expected value basically means if you do the trial 1,000,000 times and then you average the results, you expect that the average of the results is about 4.2. That's what this means. It means over, as the number of trials goes to infinity, we expect that the average trial, the average of the trials, will converge to 4.2. And so you see that that's a little bit more technical than like just saying, oh, I expect if I roll this die once, I expect to get a 3, right? Or whatever kind of expected value you might say it is. So do you need to have each thing? Yes. So basically all of the things that can be chosen have to have numerical value. It would be a little hard if I said that we have a box, a square, and a pentagon, or whatever this shape is, and I said, well, the probability of this is 1/5, the probability of this is 2/5, the probability of this is 2/5. What's the expected value of this? And you'd be like, well, it's 1/5 times box plus 2/5 times circle plus 2/5 times pentagon. Which, I mean, you can write that down. There's nothing illegal about it. It's just you can't add them. Okay. So actually, this problem is a little bit more delicate if you take away the 1 and you do 2. So let's do 2. I need a new page. So, well, in the case that I was talking about, it didn't matter because I had changed it from 2 to 1. So we were only picking 1 ball. So now we're going to pick 2 balls. And let's do it without replacement. So what does it mean to pick 2 things without replacement? Well, we have a 1 ball, we have a 2 ball, we have a 2 ball, we have an 8 ball, and we have an 8 ball. And so if I pick the 1 ball, I don't get 1 ever again. If I pick this 2, I can get this 2, but but the probability changes depending on what happens. So for this, it's actually useful to draw out a tree, and let me show you how the tree works. So the probability of picking a 1 is 1 out of 5. The probability of picking a 2 is 2 out of 5. The probability of picking an 8 is 2 out of 5. Okay. So now let's do everything again. What's the probability of picking a 1 given that I've already picked a 1? So if we want to get a 1 and then a 1, as it turns out, that's 0. Because we've already picked the 1, and so there's none left. Yeah, exactly. So you could call that 0 out of 4 if you like. In this case, what's the probability of getting a 2? Well, there's still 2 2's left. Exactly. So 2 out of 2. I'm sorry, 2 out of 4, or 1/2. Yeah, because I didn't put it back in. This is without replacement. That's what this means. And then this is also 1/2 here. Okay. Then let's do the same thing again. So the probability of a 1 in this case is 1 out of 4. The probability of a 2 in this case is 1 out of 4. And the probability of an 8 in this case is 1 out of 2. And then finally, the probability of a 1 in this case is 1 out of 4. The probability of a 2 in this case is 1/2. And the probability of an 8 in this case is 1/4. So, what is the expected value of this? So if you're slightly scared, that's good. But let's make it through. So what are the possible events? Basically, the value, and remember that we're calculating the expected value where if this is the selection for x and this is the selection for y, we care about the sum x plus y, like that. So we want the expected value of the first pick plus the second pick. And so what we're going to do is if, so like what is the value of picking 2 1s? Well, technically that would be a 2, but it's multiplied by a 0, so we don't have that one. Here, let's just ask, what is the probability of getting, say, a sum of 3? Right, so to get a sum of 3, what has to happen? There's 2 options. Either you pick a 1 and then a 2, or you pick a 2 and then a 1. So if you pick a 1 and then a 2, you're going to get the probability is 1/5 times 1/2. And if you pick a 2 and then a 1, you're going to get 2/5 times 1/4. Okay. So basically that means that we've checked off this one and we've checked off this one. This one's already 0, so we don't need to worry about it. All right, so what other possibilities are there? So what is the probability of this? So this is 1/10 plus, this is actually another 1/10. So this becomes a total of 1/5 probability. Okay. So here's another event. We get the probability that x is equal to, or x plus y, I should say, is equal to 4. Yes, I am. So here, 2 plus 2 is 4. And yes, the probability of getting that is 2 out of 5 times 1 out of 4. Just by it's essentially the multiplication principle. Basically, we're using the multiplication principle a bunch. Okay, so what's another option? So that's one option. So one other option is 9. We can have the probability of x plus y is equal to 9. And in that case, we're going to get There we go. Okay. So you get x plus y to be another number. Yes. So x plus y, you can't calculate them separately because depending on your first pick, it changes the probability of the second pick. I mean, I guess actually you could, but no. Yeah, I'm sorry. You can't do it as easily as that. So if these two things are independent random variables, then it's true, then you can separate them, but we haven't gotten to that fact yet either. So basically, I'm just curious about the things that get us to 9. So the things that get us to 9 are 1/5 times 1/2 plus 2/5 times 1/4. Which again actually is equal to 1/5, right? Because this is 1/10, another 1/10, so this is 1/5 total. And that takes care of this one and this one. So we only have two things left. We have the probability that x plus y is equal to 10. And we have the probability that x plus y is equal to 16. So the probability that it's equal to 16 is just this branch here, the 8 and the 8. So it's 2/5 times 1/4, which as it turns out is not 1/5, it's just 1/10. Same thing with this one. This is another 1/10. And so the last one here, you can either get 10 by doing 2 and 8 or 8 and 2. Either way, they're both 2/5 plus 1/2, so you get 2/5 times 1/2 plus 2/5 times 1/2. Both of those are, so we're going to get 2/5 total there. So let's make a new chart. So the sums are 2, 3, 4, 9, 10, and 16. And the probabilities of those values, so if I call this k, and I say that this is the probability that x equals k, the probability that we get 2, that we get 1 and 1 is 0. The probability that we get a 1 and a 2, I think that was 1/5. I'll check those. The probability that we get 4 is 1/10. Hopefully they'll add up to 1. The probability that we get 9 is 1/5, and the probability we get 10 is 2/5. So is this a probability distribution? Does this add the 1? Well, let's check. 1/10 plus 1/10 is 1/5. 1/5 plus 2/5 plus 3/5 plus 4/5 plus 5/5 is 1. So yeah, it does. Cool. So that means that we didn't screw up. So there's a low chance, the probability of a screw up is small.
So how frustrating would that be though, if it was wrong?
The good news is I've done this type of problem before, so I was pretty sure. Okay. But yeah, no, it's always possible that you'll make some arithmetic error somewhere in the tree.
Yeah. Or like when I spent 10 minutes debugging a live coding that I did yesterday.
Oh my.
Oh my.
Oh my, George Takei. So finally, let's compute the expected value. Well, it's equal to 2 times 0 plus 3 times 1/5 plus 4 times 1/10. So I'll just write that as 4/10. Plus 9 over 5 plus, let's see, 10. So it's going to be 20 over 5. Ah, crap. Can I zoom out just a little? No. Well, that was stupid. Okay, we're just going to smash it in the corner. 16 over 10. Okay, so this is it. So that's 0, so that dies. 3/5 is 3/5. This is 2/5, so this is 3/5 plus 2/5. Plus 9/5. Plus 20/5. Plus, and then in this case, this is 8/5. So 25 plus 17 is the same thing as, I'm going to say 43 over 5. I'm definitely saying that. (42 over 5). Now I'm saying that. So, what is 42 over 5? The answer is who knows. 8.4. Okay. So the question is this a reasonable expected value to see? And the answer is, if we kind of graph out where all the stuff is, right? Basically pretend that everything is on some kind of balance beam, right? So at 2, we have nothing. There's nothing sitting there. But at 3, we have a little weight. We have a 1/5 weight. At 4, we have half of that weight. We have 1/10. And then we go all the way up to 9. I guess here, let's make this 10 so that this can be 16. And we'll put 9 here. At 9, we have a 1/5 weight. At 10, we actually have a 2/5 weight. So a lot of the weight is right here. And then here, we have a 1/10 weight. Everything's a job for MATLAB if you're creative enough, I guess. Okay, cool. So that problem was longer than I thought it was because I didn't read the 2. I only saw the 1. So yeah, I was thinking, oh yeah, I didn't see that when I typed in the problem. I was like, yeah, this will be fun. This will be fine. This is really all I cared about. But, you know, it's a valid problem, and this type of thing this is not the last time you're going to see these types of trees. So next week we're going to do a lot more with these types of trees when we get to Bayes' theorem. So drawing this tree is kind of a hint to future things, right? It's a hint for the future. Yeah. We need 1.21 gigawatts.
Oh, I'm so glad that they know all about trees and they love them.
Trees are good.
So that when they get the 341, they'll start loving trees.
Well, I mean, we haven't done any graph theory yet.
Ooh.
But I'm gonna do some because I feel like graph theory is fun and like never gets covered, right? And you always think, I should know more about graph theory. It's just like every mathematician I've ever heard is like, oh man, I should learn more representation theory. But we never do.
Yeah. But
what? What's your excuse?
But also, every time I learn graph theory, I feel like it's taught to me in a way that makes me sad. So whenever someone teaches it well, I'm like, oh, that's very nice.
Oh,
But
graph
we're
theory.
getting dollars? You're giving us money now?
Yeah, well, apparently.
Oh. Oh, we have to pay money, though.
Yes.
Oh.
So, as a last little example, this is going to be a much easier example. So, we pay $1 to play the game. We toss a fair coin 4 times. If no heads occurs, then the person pays an additional $2. If 1 heads occurs, the person pays an additional $1. If 2 heads occur, then the person loses the initial dollar, so that they should just say $0. If 3 heads occur, the person wins $3, and if 4 heads occur, then the person wins $4. So what's the expected gain? So basically, let's write it all out in a table. No, that is offensive. Ugh, fine. No, we're gonna do this better. I swear. Ah, good enough. Wait, no, you took my line away. Okay. So, the options are either 0 heads, 1 head, 2 heads, 3 heads, or 4 heads. But that's not the value in the game, right? The value in the game is that the person pays $1 to play, and so if no heads occur, they lose $2 in addition to this $1. So let's call this value -3. If 1 head occurs, the person pays an additional $1. So that means -2, right? Because they pay the first $1 and they pay an additional $1. If 2 heads occurs, they just lose the initial $1, so we can say -1. If 3 heads occur, then they win $3. But do they get their original $1 back? Doesn't really say. Let's say that they get their original $1 back. Get their $1 back. So, and then if you and if 4 heads occurs, you win $4. So now we need to compute the probability of each of these things. As it turns out, the probability of these things are 1 out of, 4 times, so it's 1 out of 16. 4 out of 16, so this is 1/4. 6 out of 16. 4 out of 16, which is 1/4 again. And 1 out of 16. If you're curious about how to calculate those probabilities, these are the binomial distribution probabilities. So these are 4 choose 0, 1/2 to the 4th. This is 4 choose 1, 1/2 to the 4th power. This is 4 choose 2 times 1/2 to the 4th power. This is 4 choose 3 times 1/2 to the 4th power. And this is 4 choose 4 times 1/2 to the 4th power. Okay, so let's calculate. So what is the expected value? Well, it's equal to -3 times 1/16 plus -2 times 1/4 plus -1 times, I guess, 3 out of 8, if we're going to simplify, which we shouldn't, plus 3 times 4 out of 16 plus 4 times 1 out of 16. Okay, so let's see what this is in total. So this is -3/16. This is 4/16, so this is -8/16. This is 6/16, so this is -6/16. This is 12 over 16. And this is 4 over 16. So when we add all of these numbers together, so what happens if two heads occur? We lose $1. The game is definitely rigged. And we are proving it, right? Statistically, we are proving it. So let's see. 12 plus 4 minus 6 minus 8 minus 3 is, minus 1 over 16. So, as it turns out, this game has a very slight negative expected value. And so what that means is that we expect, well, 1/16 is what? 0.0625. So that means on average, per time we play, so if we play n times, we expect to lose about 6.25 cents times the number of times we play. So that's what this expected value means. It's very slightly negative. We expect to lose on average 6.25 cents every time we play. We know that's not actually what happens, right? We don't lose 6.25 cents at any point, but what really happens is that if you just play this game a whole bunch of times, it'll average out to this. So remember that this is an average. This is not actually a this is not a probability of a single event or anything like that. Okay, cool. All right, so I've kept you too long. So the good news is we'll end lecture. I'll send out a practice test probably sometime tomorrow. I'll try to write it up tonight. And no, I'm not scamming you. The game is scamming you, Kevin. I am providing you with extra instruction. So actually, the expected value of your college is positive now.
It wasn't looking so good beforehand, but it's better now.
Yeah, it's slightly better now. So I'll go over what the exam covers on the practice test. So I'll give a list of topics and that kind of thing. So, okay. Basically, it'll cover everything through today, I guess. Everything up through expected value, maybe. So the definition of probability all the way back to whatever we did before, right after the first exam. So all this counting stuff and that kind of thing. Okay. All right, everyone. All right, Ben. It's a pleasure to have you along as usual.
Oh, I love being the first officer on this starship of math learning.
Oh yeah, it's terrifying, isn't it?
Yeah.
But in the end, it's really not as painful as you think, right?
No, it's good. This is all very important stuff.
Yeah.
And everybody got to learn to love trees and how cute they are.
Yeah, trees are good.
And we're totally not going to make them feel differently about that in 341, are we? Are we, Eric?
Oh, certainly not.
No, they're going to love trees even more.
I think 341, the actual course title is Trees and Why You Should Love Them.
I call it Advanced Connect the Dots, but I like that title too.
So, okay, in terms of the last two questions, when we'll post the quiz grades on Blackboard. Oh, yeah. So I think it's possible that there's a set of quizzes still sitting in my office, so I'll have to actually drive into campus to get them. They are graded, they're just not entered. In terms of giving out book problems, my anticipation is that I was going to release a homework today. So that homework won't precisely be book problems, but it's like book problems, and you can find book problems that are like that. So, yeah. Okay. Advanced Connect the Dots. Okay. All right, I'm gonna... Yeah, I can leave them there. Everyone, I think people all did relatively well, so I'll get them eventually. Did I get the exam ones from SDS? Yes, I did. I will grade them probably tonight or tomorrow. Chapter 9 is mostly the exam, yes, since all of this stuff is in Chapter 9. Okay, everyone. That is a lot of administrative questions that you had right at the end, so that's excellent.
Oh, it's time for them to go enjoy the weekend.
I know, right? It's like, get out of here. Go have dinner. Go, I don't know, talk to your loved ones or whatever it is you do to them. So, all right. Have a good night, guys. Bring Lysol wipes. Yeah, I don't anticipate actually talking or seeing anyone. I'm just going to go directly to my office. So anyway, all right.
All in a day's work for us, right?
Yeah, exactly. All right. Bye, everyone.
Bye, nerds.
Yeah. So what should we talk about in the outro now?
I don't know. Something exciting about birds.
I know nothing
found out
about
that
birds.
Kookaburras are in the kingfisher family. How exciting is that?
That makes sense.
Yeah, they kind of look like kingfishers.
Exactly. They're like mini ones, right?
I think they're probably larger than the average kingfisher.
Oh, okay. Maybe I just don't know anything about birds.
Yeah.
It's true.
Yeah. We're straight lo-fi. Do you hear that? Do you see that? We're lo-fi. Is it still recording?
Oh yeah, no, we're still broadcasting because. Because
no.
I mean, the moral of the story is that we always should just broadcast straight over the outro and then have a conversation afterwards and pretend
in the darkness.
Yeah, pretend like it's totally unintentional. Exactly.
This is candid. This is candid recording.
Exactly.
It's part of the outro. Yeah.
Right.
Yeah. That makes sense.
So, do you anticipate?
We should actually do a podcast. I've been trying to get this guy to do a podcast with me.
Yeah, it's gonna have to be Eric Explains the World, and then Ben asks him a bunch of questions about what the hell he's talking about.
Yeah. This was Eric Explains the Universe, and then I go get some horrible misunderstanding about science, technology, politics, or law from Wikipedia, and then Eric sets me straight.
I do a lot of that.
Yep.
Oh man.
Intentional blooper. Oh yeah.
Yep.
All right. Should we release them from?
Absolutely. We're gonna end this stream. You know why?
They want to know. They want to hear you talk about politics. I don't think they do.
I mean,
I've heard it a lot.
If you don't mind a slight bit of crying at this point and maybe some unintelligible screams of horror, then sure, politics sounds like a great topic.
Yeah. That's how I feel as well.
I just like that this is still going onto the YouTube video, so if people actually watch it past the end, they're gonna get this nice little surprise.
This is like how they used to do on, I don't know if many albums still do this because it's mostly like Spotify and stuff, but like if you listen past the end of the last track, there'd be silence, and then there'd be like a super secret hidden song.
Oh yeah. That's like lo-fi vinyl land, man.
Yeah, we're in secret song country.
Or especially on like a cassette tape.
Oh yeah, this is where like you've already turned it over. You've already followed instructions, and now this is like the secret thing, the secret bit.
Yeah, exactly.
Did you have any of those things as a kid where it was a little storybook was like a picture storybook, and there was a little cassette that you could put in to listen to it while you were? Did you have that?
I don't know if I ever had that.
Okay, it was like having someone read a book to you, except if.
No, I mean I can imagine what it is. I had the Sesame Street vinyl record player 45 player.
You had See, I had Sesame Street cassette tapes, so you were way more legit. You're like a Sesame Street hipster.
Yeah, I mean the problem with my parents was that they had all this extra vinyl, and so they let me as like a 4-year-old play with it. I can't believe that they did that.
Well, it wasn't worth anything then.
Well, yes, that's true, but also it's also my father, right? Who
that's right.
I recently saw a video of me when I was a small, like, toddler baby thing, and he didn't care that I was playing with all this stuff until I ripped the cellophane off of one of his cassette tape boxes. And
Oh,
that was
that's a
what did it.
progression.
He was done after that. He was like, I can't believe he did that. I mean, of course I was
I
2. Like,
Yeah.
you know.
The only video I've seen with me as a child, I was like 4 or 5 years old, and it was Christmas Day, and they were giving me presents, and I was opening them,
Yeah.
and I had no expression. And I remember I remember opening up like the one big present that I got. I was so excited about, but if you watch the video, no expression. I open it up, I look at it, and then I like thank my parents and I set it down. Like, I'm surprised my parents didn't think I would be an axe murderer or something.
Yeah, maybe they took you to a psychologist or something. And they're like, he has low emotional affect. He doesn't seem to be like empathetic at all.
No, and then I asked my mom about it, and she's like, "Oh no, the way you would be excited is I would apparently just shake, which just never came through on the video, but like I would get this full body like nervous shake when I was excited." So, yeah, we're strange birds. We'll just make these into podcast sessions. That may be the plan. This will be our podcast. Anyway, I had a cassette. Speaking of being a young baby, I had a cassette thing with the Sesame Street.
Yeah.
And I loved them all. I like basically wore the cassettes out, except one of them, Bert and Ernie got in a fight. They got in like an argument. I never listened to that one. That one made me nervous. So I was very conflict averse, even as a little bebe. I was like, ooh, I don't like it when Bert and Ernie fight. I want them to be happy and love each other. So, yeah. Oh, there's still people here. There's 13 of you. Have nothing better to do.
In their defense, if I knew that if Edelman had a live stream, would you listen to that?
I would never do anything else.
Hell yeah.
But I don't know. Are we Edelman quality? I don't know.
Well, I think our current material's been okay.
Oh, Jennifer gets it. Yeah, the plastic bag and the book and the cassette. And the plastic bag had those crappy little white plastic handles on them. And that was the stressful part about returning them, is because they had these little plastic interlocking handles that you had to just fit together just so. There were these little nubs. And it was kind of stressful because you're like, if you don't get those little nubs, little interlocking correctly, I always felt like they were going to find me or send me to some sort of Sesame Street library book prison for kids who can't reattach handles together. Ugh.
Yeah, I mean, in terms of vinyl, the real issue is when you're 4 years old, you don't have the hand-eye coordination, and so you end up like, you don't pick up the head of, the tone arm properly, so it scratches across the surface of the record, which is something that, I mean, I think my father has killed people for.
Yeah.
So I don't know how I survived childhood, but I suppose forgiveness happened. Maybe there was an exception for, So I can't imagine that there would have been an exception for being his son. Like, that's not sufficient for scratching a record.
You've been Scratch Master Eric for longer.
Yeah, I think. Yeah, I mean.
Yeah. Because normally I see you with the big headphones and you have the glow sticks around your neck.
Oh yeah,
and you're sitting between the big speakers.
And I have
sunglasses on in the really dark clubs and stuff.
I have two SL1200s for scratching.
Yeah, exactly. That's usually where I'm used to seeing DJ Eric.
Yeah, that's
outside
right.
of class. You're either spitting math truths or you're scratching some records.
You got me pegged.
I didn't know it started at such a young age, though.
Sometimes you can even record math onto vinyl. And then there is a potential that it will open a black hole into a parallel universe where everything is good. Kind of a Leibnizian best of all possible universes.
Mm-hmm. This is why you're DJ Hamilton.
Yes.
Or Eric. Would you be DJ Hamilton or Eric, or would you have a different DJ name?
I'd probably be like DJ E.
I think that's where we end it. I think that's where we call this. We call this a lecture.
All right, lecture terminated.
Terminate.
Bye, everyone.